As we wrap up the notes on IMS, we are looking at how the visible spectrum connects with what we can know about solutions and even solids or pure substances maybe in the liquid state. In a flame test, we are adding heat to allow an element to have its electrons jump up and down, releasing a color of light that corresponds to a certain wavelength, therefore frequency there and energy between those energy levels. Some things have color without the necessity of a flame test. Solutions are good examples of this. Right here is a picture of solutions of several different transition metals. Transition metals often are colored because of the energy associated with the filled or partially filled d orbitals. So transition metal ions have energy differences between those d orbitals that tend to correspond to visible light. The whole mechanism of when, how, why we would explain this is not especially important. Just knowing that it's the transition metals that are most likely to be colored. And when we think about their color and what we know about their color, that connects to the light it absorbs and the light it transmits. So the reason a cobalt solution looks pink is that it absorbs white light. The light that makes it through is pinkish, and all of the other colors, or those complementary colors, are absorbed. That absorbance and transmission is something we can see, but that absorbance and transmission is also something that we can measure. Beyond just thinking about what is green, orange, red, or blue, we can think how light or how dark is the color of a solution. We have all experienced this difference as we add more and more of a solvent, be it Kool-Aid to something, or we take a liquid and we water it down and its color gets lighter and lighter. The intensity or the darkness of that color changes based upon the concentration. That relationship between concentration and the color we observed is defined by Beer's law. Beer's law is right here. A, the absorbance, or how much light that solution blocks, is related to epsilon. Sometimes you'll see it as a lowercase a, but epsilon, the molar absorptivity constant, which is a constant related to the wavelength of light that we are looking at. So for a specific element, vanadium +2, for example, it would have a different constant for each different wavelength that would correspond to the fact that it absorbs a lot of yellow while transmitting blue and red to make a purple solution. B is the path length, and this connects probably with something that we've seen. When I have a small or a thin sample of something in a small piece of glassware, the color might not be as dark as if it's a larger beaker. When we are testing absorbance, we often use small cuvettes that are about 1 centimeter across, and that's how far or how much solution our light has to go through to see the absorbance. And lastly is the concentration. The concentration is normally given in molarity, but there are different units we can use, and all work here, that there's a relationship between any concentration unit and the intensity or absorbance of that color. We can kind of look at this generically, but most of the time we want to look at this graphically. So we want to see at different absorbances what concentration we have, or most likely at each concentration, what is my absorbance? We can create a calibration curve. When we do that, we take a solution that I know the molarity of 0.1. I measure its absorbance. 0.2, I measure its absorbance. 0.3, I measure the absorbance. 0.4, I measure the absorbance. Because absorbance is actually the log of how much light gets through, we often want to be between the 0.1 and the 1.0 in our absorbance there. So if we're outside that range, we would do something to change our solution to get it within that range. But I could then take an unknown solution, measure its absorbance, and either with the graph or by applying the equation, I could find for a specific absorbance, maybe 0.4, drop down and see what molarity that corresponds to. Before we do that, we often look at a absorption spectrum for that element to see what colors of light does it absorb a lot, what colors does it transmit a lot. So when we look at this one, this transmits or lets a lot of the yellow through. The solution would look very yellow, meaning it absorbs purple, blue, and red even more. So when we are then making our calibration curve, we would want to use a spectrophotometer or colorimeter that is set to a place where we're going to have a very high absorption, either over here in the 450 range or over here in the 650 range. We also, as we'll see in the questions, need to make sure that we don't have any other compounds, any other elements, or any other colored things in our solution that would throw off our calibration